So this is lesson 4.3, where we're going to build on what we learned about two variable statistics previously when we talked about scatter plots, and we're going to talk about correlation and causation today. So we already know from 4.2 that when researchers investigate relationships between variables, we have specific words to define those variables. So our explanatory variable, that goes on the x-axis, and that is going to be what explains, or in some cases, as we get further in this unit, predicts what the response is going to be in our y variable. And then, notably, our y variable is named the response variable. And that is what we're trying to explain a relationship about or make a prediction about what that variable is going to be, because when we're doing two variable statistics and we're looking at two quantities, those two quantities are not necessarily related, and they're not necessarily explanatory and response in terms of that relationship. So what we're trying to do when we do this research and then we analyze our data is see whether or not there's a correlation. A correlation describes a relationship between those two variables, but without suggesting that one variable affects the other. So here's what this means. This means that when we look at our explanatory and our response variables, they might show distinctive patterns with each other. There might be a relationship there, but we cannot definitively say that X causes the change in Y. So when we're looking at research headlines or we're looking for a suggestion that it's correlated, these are the vocab words that we're looking for. If the explanatory and response are linked, if they are tied, if they tend to cause a change, that's a correlation. So when you see these vocab words, we're specifically identifying a correlation between two variables. Now, this is different from a causation. When we talk about a causation, we are saying that one variable directly affects the other. X causes the change in Y. That is different than just having a relationship. If they have a relationship, one doesn't necessarily cause the other. If we have a causation, then our X variable is directly impacting our Y variable. So vocab words we're looking for: cause, increase, decrease, benefits, effects, an if-then relationship. And this is really important because when we're looking at causation, or we're thinking about a relationship between variables where one directly affects the other, we have to be careful of our lurking variables. And we briefly discussed these way back in Unit 1 when we talked about collecting data. Lurking variables are factors that are outside of what's being investigated that might impact the relationship that we're seeing. And we're going to take a look at some examples right now that's going to help you understand the difference between these. So here's what we're going to do. In just a moment, I'd like you to pause the video, read the research headline that I've given you, and determine if the headline implies correlation or causation. Identify your explanatory and your response variables based on the headline. And then, if you decided that the headline implies a causation, and only a causation, not for a correlation, I want you to identify a lurking variable, something outside of what was being studied that might contribute to that relationship. So go ahead, pause it, try them for yourself, and then unpause the video and check and see how you did. If you didn't do well, please don't panic. These are just notes. I just want to give you guys an opportunity to see how much you remember and how much you know right now. So Hopefully you did that and you didn't just skip to this part, that you paused and you actually took a moment for yourself. If you didn't, well, here we are. We're going to go back to these lists of vocab words that we've identified, and we're going to use those to help us determine if the headline implies correlation or causation. So music lessons improve kids' brain development. Improve is one of our causation words. So this headline is implying causation. Our explanatory variable, our X variable, would be whether or not a student has music lessons. Our response variable is a kid's brain development. So this headline is implying that if you give your kids music lessons, their brain is going to develop better. However, there are definitely some lurking variables I can think of here that would have an impact on this relationship. For example, family income. It would help if I spelled that right for you guys. If a family has enough extra income to pay for music lessons for their kids, that family probably also has extra income to afford a better quality of life and have better access to things that are going to help their kids' brain develop better. Maybe these music lessons come from school. This could also just be directly related to the quality of the school the kids attend. We know that arts programs are one of the first things that schools cut when they're struggling with their budget. So a school that has a rigorous enough arts program to have music lessons available for the kids cares about the education their students are getting, which means it's probably a higher quality school, which is helping the students' brain develop. So those are just two examples of lurking variables for that example. So the second research headline, positive attitude tied to academic success. When we take a look at our vocab words up here, tied is a correlation. This is not implying a causation. The positive attitude is our explanatory. The academic success is our response variable. And because this is only implying a relationship, it's not saying that positive attitude causes academic success. We don't need to identify lurking variables. We're not looking for a causation here. The third one, low self-esteem related to unemployment. Related to, that's also a correlation vocab word. Self-esteem would be the explanatory variable. Unemployment would be the response variable. And again, because this is implying a relationship and not a cause and effect situation, we don't need to identify a lurking variable. Then the last one, if you have stock investments, you will be happy. This is an if-then relationship. If you have stock investments, then you will be happy. That's a causation vocab word. So stock investments would be our explanatory variable. Hopefully we've picked up by now that the explanatory variable comes first in each of these headlines. If we didn't pick up on that, there you go, I've highlighted that for you. The response variable here would be happiness. But there are a lot of reasons why stock ownership might cause happiness here. Again, like the first one, having extra money available. I know they say money isn't everything, but having extra money available to be able to make more stock investments, that's probably going to make someone pretty happy because that money is not only funding their stock investments, it's funding other aspects of their life. It also could just be someone's personality. There are certain personality traits that make people more likely or less likely to put money into stock investments. It could be that the personality traits that contribute to someone having more stock investments also contribute to them being happier in general. So that's identifying correlation versus causation in a headline or in a given study that we're looking at. When we talk about correlation, that is our primary focus of this unit when we're looking at scatter plots. We have a mathematical way of quantifying the relationship, and we call it the correlation coefficient. We represent it with a lowercase r. We use this number, the correlation coefficient, to describe the direction and the strength of a linear relationship between two variables. So if you recall from lesson 4.2, we talked about form, direction, and strength being the big three things that we need to comment on when we're talking about our scatter plots. This number will help us identify two of those things. We are going to always use technology to find that correlation. If you remember back to our Vitruvian Man example, I briefly showed you what the equation looks like in order to find correlation by hand. We are going to take a look at that formula here right now in the notes. You will never have to do this by hand. However, understanding this formula helps us understand some things that are really, really important to know about correlation. So, deep breath. This is a big one. Our correlation coefficient is equal to 1 over n minus 1 times the summation of every individual x value subtracting the mean divided by the standard deviation of x times every individual y value subtracting the mean for y divided by the standard deviation of y. Horrible. Disgusting. Can't even believe we're looking at such a long equation. When we break this down, n is the number of xy data pairs. R is our correlation coefficient. X sub I and Y sub I are each individual x value and each individual y value. X bar and Y bar are the means of the x values and the means of the y values. S sub x and S sub y are our standard deviations. If you were asked to do this all by hand, you could do it. You have all the formulas available to you. However, it is such a horrific process when our data sets are large. We are going to use technology via Statlet. So essentially what this is doing is it finds the average of the product of the standardized scores. So we standardize things, we multiply the x and the y standards together, we add them all up. That gives us our correlation coefficient. This helps us describe a possible relationship. And that's kind of the funny thing here. It's not even guaranteeing that there's a relationship between our variables. There might be a relationship. So we're going to do all this math to figure out if there is a relationship or not. When we talk about correlation coefficient, there are 7 facts that you need to know. The first one is that your correlation value is always a number between -1 and +1. If we have a correlation of r equals -1, that is a perfect negative linear relationship. So here's what that means. If I have a line of best fit, if it is a perfect negative linear relationship, r equals -1, every single one of my data points falls on that line of best fit. It is essentially as if I gave you an equation for a line and I had you graph it. Now this line has a downward slope. Please note the slope value does not determine the value of R. That line that I just drew doesn't necessarily have a slope of -1. It could have a slope of -3. It could have a slope of -1/2. As long as it has a negative slope and all of the points fall on that line, our correlation coefficient is -1. In the same scheme of everything, but on the positive end of things, if I have a correlation coefficient of +1, that is a perfect positive linear relationship. So very similar to what I just did for R equals -1, if we draw a positive line, that means that every single one of my data points falls on that line. Again, this line doesn't necessarily have the value or the slope value of 1. It could have a slope of +2. It could have a slope of +100. The point is, it's positive, and all of the data values fall on that line. That's what gives us a perfect positive linear relationship. Because when we talk about correlation, we're talking about the relationship. Now, if R equals 0, it means that we don't have a linear relationship at all. There's a couple different ways this could look. One of these ways is just that we have points everywhere in our scatter plot. There is no definitive positive or negative direction. These points are pretty much everywhere, and if you tried to draw a line of best fit, you would probably get something that's pretty similar to this, just a horizontal line. Because there is no linear relationship. Those points don't form a line, it's just a cloud of data. So, fact number 1, the correlation value is a number between -1 and +1, always. You cannot have a correlation outside of those values. Fact 2, if it's a positive correlations are always between 0 and +1, and they have varying strengths. The closer a positive correlation is to +1, the stronger it is. So here's what we're going to do. For each of these examples, we're going to draw the same line. All of these lines are positive. If we have a weak positive linear relationship, then we have points that are fairly spread out from that line of best fit. You might have one or two that are closer to the line than others, but for the most part, our points are in an upward direction, but they're fairly spread out from that line of best fit. Now, if we have an R value closer to +1, like an R value of 0.9, that means while our points aren't perfectly on the line, they're going to be pretty close. You might have one or two that are on the line. You might have more than that, depending. But those points are distinctly tightly packed around that line of best fit. And then, like we talked about yesterday, we have moderate positive linear relationships, and those are going to fall somewhere in between these two. They're not all tightly packed around the line, but they're definitely not as spread out as our weak relationship was. Here's the catch. When we're looking at weak versus moderate, moderate versus strong, there's not a magic cutoff number. Nobody is standing here saying that if it's between 0.45 and 0.75, then that's guaranteed to be moderate. It doesn't work like that. You have to go with your gut, and you have to look at how those points are spread out to determine whether or not it's weak versus moderate or moderate versus strong. There's not a cutoff number I can give you that's going to help you with that. Now, here's the good news. Fact number 3, very similar to fact number 2. Negative correlations are between -1 and 0 and have varying strengths. The closer a negative correlation is to -1, the stronger it is. So we're going to do the same thing we just did with fact 2. We're going to draw the same line 3 times. And then we're going to describe what those points look like. So if we have an R value of -0.9, that's fairly close to -1. We're going to have our points that are fairly tightly packed to that line of best fit. You might have a couple that are directly on the line, but they're not in a perfect line. They're just really tightly packed to that line of best fit. Now, on the other hand, if we have an R value of -0.3, these points, while being distinctly sloped downward, are pretty spread out from this line of best fit. There's a cloud of data. And we can tell that it definitely slopes down, but our data is not packed tightly to that line. And again, if we look at the moderate relationship, they are definitely closer to the line than the weak relationship was, but they are more spread out than the strong relationship is. Again, there's not a magic cutoff number I can give you here. You have to go with your gut describing weak versus moderate, moderate versus strong. Fact 4. When we talk about correlation, correlation only describes linear relationships between two variables. So remember, think back, way back 2 pages ago, when I said you could have an R value of 0, and that could be no linear relationship and a cloud of data. There are other situations where we have a correlation value of 0, and this is one of them. Many students are tempted to say that this scatter plot has a correlation of -1, because if they trace this point, or these data points, we have a perfect negative quadratic. Correlation only describes linear relationships. This is not a true statement. If we were to say it is a perfect negative quadratic relationship, it does not have a correlation of -1. This is a quadratic. It's not linear. This would have a correlation of 0 because it's not a linear relationship. Correlation only describes linear relationships. Just because you have a perfect negative or a perfect positive, if it's not linear, it's not a correlation value. Correlation only describes linear relationships. When we look at fact number 5, correlation does not have units. This is coming from the formula. If we change the units on either axis, it's not going to affect the correlation. So if we think back to Vitruvian Man, I had you measure your height and your arm span in centimeters. If I changed my mind tomorrow and I made you measure your height and your arm span in inches, our line of best fit and our correlation value would not change. They would stay exactly the same because correlation does not have units. This is because when we look at this formula, we are standardizing those scores. If you think back to z-scores, when we said we were standardizing, this is the same process. and z-scores didn't have units because they canceled out when you divided the top by the bottom. Correlation does not have units. Your units cancel when you do the standardizing process. Also, built from the formula is fact number 6. Switching the position of the explanatory and the response variables on the axes. So if I put the x value on our y-axis and the y values on our x-axis, it's not going to change the correlation. When we built our scatter plot for the height and the arm span, we put height on the x-axis and arm span on the y-axis. If we switched those tomorrow and we put arm span on the x-axis and height on the y-axis, our correlation would not change, our line of best fit would not change, because switching which variable is on which axis does not change the correlation. Here's why. When we look at this formula, you are multiplying here. Multiplication does not have order of operations. The order of multiplication does not matter. In case I've lost you, here's what I mean. Think to yourself, what is 2 times 3? 6, right? What if I switch those two numbers? If I do 3 times 2, have I changed the multiplication process? The answer is no. Those are both 6. It does not matter what order you multiply those standardized scores in. Because you are multiplying, we can switch the position of the x and the y variables on the axis, and it's not changing our correlation. So in reality, it makes no difference which variable you call x and which one you call y when you're calculating correlation. It might matter when you graph it for your scatter plot, but it does not matter for your correlation calculation. Okay, and the last fact, correlation is very strongly affected by outliers. When outliers appear in your graph, we need to be cautious about using our correlation. We are not going to rely on correlation alone to determine linear strength. We're not just going to look up the R value for our data and say that that must be the end-all be-all, positive, negative, linear relationship, whatever it is. First, we're going to graph the scatter plot. The good news for you all is that in order to calculate the correlation on Statlet, you have to graph the scatter plot in the process. When we look at the scatter plot, we should be able to see whether or not there's any visible outliers. And if there are, we are going to proceed with caution because outliers are very powerful when we talk about correlation. One outlier can significantly alter the line of best fit and thus alter the correlation. Okay, last piece of this unit. Correlation tells us the two variables are related, but cannot officially tell us that one variable caused the change in the other variable. If we want to imply cause and effect, we have to do a true experiment. If you think back to Unit 1, that was when we were using our simple random samples, our blocking, where we were setting up experimental groups with different treatments and we were randomly assigning people to a treatment. If we truly want to discuss cause and effect, it has to be done with an experiment. It cannot be done with an observational study. We can comment on correlation all we want. What we can't do is talk about cause and effect. Here's a really popular example of that. I am guessing that some of you have heard that having a glass of red wine is good for your heart health. That having a glass of red wine every once in a while is good for your heart. Here's the catch. That is not true at all. All alcohol is carcinogenic. Alcohol is not good for your body, but But here's what researchers didn't do when they made that statement. As it turns out, when we do more research into that, what we find is that people who have the money to be able to afford a nice glass of red wine every once in a while also have the money to afford better health care. There is a huge lurking variable in that study that researchers did not identify for years. So here's what you're going to do. There's some misleading causation headlines here. I want you to take a look at what the results were with their correlation coefficients. I want you to take a look at what the headline says, and I want you to think, what are the lurking variables that are not identified when we're just talking about correlation? So pause the video, try it, and then unpause the video and we can go over it together. Okay, hopefully you're back from trying it on your own. If not, that's just a learning opportunity you're stealing from yourself, but we'll check it anyway. The first thing I would do looking at this is identify form direction strength. This has an R value of 0.95, strong, positive, linear. Same thing with the ice cream sales, R value of 0.82, strong, positive, linear. The cavities in elementary school children, strong, negative, linear. It's got an R value of negative 0.88. All of those correlation values suggest a strong relationship. So for the first one, they did this study, and they said that a higher education degree leads to higher paying jobs. Probably not. What's more likely here is income. And that's income before the higher degree. If a person has the money to pursue a higher degree, then they probably already have a decent paying job. If somebody has a higher income and they are able to afford a higher degree, they likely already have access to more money and higher paying jobs as a result. Okay, correlation between ice cream sales and death from drowning is R equals 0.82. So what they say in the headline is that ice cream causes you to drown. There's a huge lurking variable here. Think about it. When do you eat more ice cream? During the summer? When do more people go swimming? During the summer. The season is the lurking variable. More people eat ice cream in the summer? More people go swimming in the summer. Just because you eat ice cream does not mean you have a higher chance of drowning. That's not how it works. If researchers do this and they don't account for the season, that's a problem because there's a huge lurking variable. All right, and the last one was a negative correlation. They say there's a negative correlation between the number of cavities in elementary school kids and their vocabulary size, so how many words they know. And so the headline says, want to avoid cavities? Get a larger vocabulary. Surely it's that easy, right? Just study some extra words and your teeth will be afraid to get cavities. Wrong. Age is key. As kids get older, they do two things. they get better at brushing their teeth. And as kids get older, they learn more words. Learning more words doesn't prevent cavities. It's just when we look at older elementary school children versus younger elementary school children, they're better at brushing their teeth and they've had a longer time to learn things. So here's the thing. When we're doing studies like this, when we're identifying correlations, it's not that numbers lie. People lie, or they seek to mislead. This might be conscious or this might be an unconscious thing that people are doing. There are people who genuinely do this research and see these correlation values, and they think that that absolutely means something mathematically and they have to share it with the world. And it's not that it doesn't mean anything mathematically, it's that they're not considering all aspects. People are often wrong, they're inexperienced, they're short-sighted, they're not looking at the bigger picture, or they're biased when it comes to interpreting data. People want their data to prove themselves to be correct. It doesn't feel good to have a hypothesis and be wrong. They are desperate to be right. But sometimes that means that they look at the data and they interpret it in a way that hides their agenda and unconsciously or consciously supports their agenda and isn't honest with the general public. So what we need to do, and this is something I really hope you take away from this class, when you are looking at data at any point in your life, whether it's on the news, social media, anything like that for your job, always look at the data and how it was collected. Don't just blindly think that everybody understands the numbers they're talking about. Oftentimes people don't. And it's not necessarily that they're trying to lie to you, but statistics is hard. And it's even harder to explain statistics to people who may not understand it. So, as you move forward, just be aware. Always look at the data and how it was collected. Don't just blindly trust. Otherwise, you get headlines that say ice cream causes drowning deaths. And that sounds really scary. And you don't want to eat ice cream because you don't want to drown. But it's not true. So you always have to ask yourself, what is this data telling me? That's the end of 4.3. Do your 4.3 practice. Have a great day.